The last part of the program, we saw that chemical plants are composed of systems. While each of these systems is made up of several different types of equipment, and each type of equipment performs a specialized function to help complete the process carried out by the system. In this part of the program, we're going to look at some of the equipment commonly found in most chemical plant systems. We'll cover this equipment to see the function each type performs. Later, we'll see how each type of equipment is used in various plant systems. Most equipment found in chemical plants is designed for systems dealing with fluids. Fluids can be either liquids or gases. Almost all systems dealing with fluids contain tanks, so let's start with them. The function of most tanks, like these, is to store fluids until they're needed. As with most equipment used in chemical plant systems, tanks come in a wide variety of shapes and sizes. For example, some tanks are open at the top. These particular tanks are designed to hold wastewater. Other tanks are sealed. Some sealed tanks, like these, hold liquids. Other sealed tanks are designed to hold gases. Now, fluids usually flow to and from tanks and other pieces of equipment through pipes. Like tanks, pipes come in different sizes and are made of different materials, depending on what runs through them. The rate at which fluids flow through pipes often needs to be controlled. This is usually done with valves. The function of valves is to start, stop, or regulate the rate of flow of fluids. Valves, such as this one, start and stop the flow of fluids. Other valves, such as these, regulate the flow rate of fluids through pipes. Plants use a variety of methods to move fluids through pipes and valves. The method used depends on whether the fluid is a liquid or a gas. Liquids are typically moved by using devices called pumps. There are many different types and sizes of pumps used in chemical plants. For instance, these are designed to pump about 30 gallons of liquid a minute. This larger pump moves hundreds of gallons a minute. In order for pumps to operate, they typically have motors. The function of motors is to provide the driving force for the equipment they operate. Like pumps, motors come in many shapes and sizes. Large models, such as this one, can produce 200 horsepower or more. This small motor, on the other hand, puts out about 1 horsepower. The size of the motor used and the amount of power it produces depends on the size of the device it powers and on the amount of material the device moves. Now, pumps move liquids, but other methods are used to move gases. Probably the most common way to move gases is through the use of pressurized tanks. Gases are often stored in tanks under pressure, and the pressure itself provides the force to move gases through pipes and valves from one place to another. Gases that aren't stored under pressure are handled differently. They're usually moved by fans, like this one. Air is an example of a gas that's often moved from one place to another in a chemical plant by fans. Air and other gases are also moved by compressors. However, the function of most compressors is to increase gas pressure so that the gas can do work. For example, a compressor might be used to produce pressurized air that's used by air-operated valves, such as this one. So far, we've discussed equipment designed to store, move, or control the flow of fluids. But there are many other devices in the plant designed for different applications. For example, water and other fluids processed in chemical systems often must be heated or cooled. Heating and cooling frequently takes place in heat exchangers. This is an example of one of the most common types of heat exchangers. It's called a shell and tube heat exchanger, and this particular one heats a liquid. This cutaway illustration shows some of the typical parts of a shell and tube heat exchanger. This is the shell, and these are the tubes. In this particular heat exchanger, steam enters the shell and passes around the tubes. The liquid to be heated flows through the tubes. The steam and the liquid don't come in contact with each other, but the heat from the steam passes through the metal of the tubes and into the liquid. So the liquid heats up as it flows through the heat exchanger. This is an illustration of another heat exchanger that's very similar to the one you've just seen. But this heat exchanger cools a liquid. In this heat exchanger, the liquid to be cooled flows through the tubes, and cool water flows through the shell and around the tubes. The cool water and the liquid don't come in contact with each other. Heat from the liquid passes through the metal of the tubes into the water. This heat is carried away by the cooling water, so the liquid cools down as it flows through the heat exchanger. Shell and tube heat exchangers are very common in the chemical industry. There are several other types of heat exchangers that are also commonly used. Here's another type of heat exchanger. It's called a cooling tower. Cooling towers cool water with air. This illustration shows the major parts of a cooling tower. The tower contains fans, spray pipes, plates, and a catch basin. This pipe carries water from a plant system into the tower. Here, spray pipes spray the water onto the upper plates. The water then cascades down from plate to plate. Angled plates on the outer edge of the tower keep the water in the tower. These slots let in cooling air. The air is drawn into the tower and through the cascading water by fans. As air passes through the hot water, it carries away much of the heat contained in the water. The cool water then settles in the catch basin and is pumped back to the plant system. As you've seen, there are several types of heat exchangers, and their principles of operation can differ. But the function of all types of heat exchangers is the same. They heat or cool fluids. Many of the fluids that flow through plant equipment must be relatively clean or free from impurities. Filters are used to remove impurities. This person is working on a filter that removes impurities from fuel oil. In general, impurities are removed because they may cause damage to plant equipment or interfere with chemical processes. These larger filters also remove impurities. They remove impurities from water in a water treatment system. Well, we've taken a look at a lot of equipment up to this point. Knowing how your equipment works and how to operate it properly is an important part of your job. Now that we've talked about equipment, we'll move on next to a more detailed look at the plant systems that are made up of that equipment. The systems we'll cover first are a water treatment system and a steam generating system. Both of them are found in just about all chemical plants, and we'll look at them in the next part of the program.
Usually when I mention safety to someone new on the job, I get one of two reactions. I either get a big yawn or instant fear. The person either has a careless attitude because he doesn't understand the hazards of the job, or the person gets scared and makes the job out to be much more dangerous than it actually is. The truth is that if you have the right attitude and respect the hazards of the job by following safety procedures, you're probably safer working here than you are working in your own home. What we're going to do now is look at some of the general rules about safety. I'll show you some of the hazards you have to watch out for and the safety procedures you should follow when doing certain jobs. And we'll also look at some of the safety gear that helps prevent injuries. So let's not waste any time. Let's get to it. Hi. One of the things we'll go over today is work clothing and personal equipment. Then you'll understand why you've got to wear certain gear and why you've got to follow certain procedures that the company requires for your own safety. Now, wearing the right clothes or using personal protection equipment may not prevent accidents, but it will prevent or minimize injuries if you do get in an accident. For instance, at least 10% of the injuries people receive on the job involve their toes or feet. That's why you're required to wear company-approved work shoes. Now, there are several types of work shoes. Most of them have non-skid soles to help prevent you from slipping on wet or greasy floor surfaces. Some, like the ones I'm wearing, have steel toes. This steel reinforcement keeps your toes from being crushed if you happen to drop a heavy box or a tool on your foot. Now, the pants and shirt you wear are also very important. The ones I'm wearing are made of cotton, but they could be made of any other material as long as it's not synthetic. A synthetic material like polyester can melt on your skin if you get caught near a fire. How you wear your clothes is also important. You want to make sure that your pant leg covers the top of your shoe, so that if you spill anything, it's less likely to get into your shoes. If you're wearing a long sleeve shirt, as I am, you want to make sure that the cuff is buttoned and that the material isn't frayed. And you want to keep your shirt tucked in. If you get a loose cuff or a shirt tail caught in the spinning parts of some machine, you could lose an arm or even get yourself killed. So dressing right isn't just a matter of being neat. It could save your life. Now, for some jobs, you may need to wear gloves to protect your hands. Cotton gloves are often used on the job to protect hands from scrapes, cuts, or blisters. Leather gloves are more durable than cotton ones and are generally used for heavier jobs. Heat-resistant gloves are used for jobs where you're handling hot materials. And rubber gloves for jobs where you're handling acids and other chemicals. It doesn't take much to figure out why you have to wear one of these. If something lands on this hard hat, it's more likely to bounce off the shell than to sink into your skull. Look inside here for a minute. You see this piece here? It's an adjustable headband. You can adjust it so that the hat fits snugly on your head. A hard hat won't help you if it keeps falling off. You see this material here? That's the webbing. There should always be a space between the webbing and the hard shell of the hat. The space acts as a cushion, absorbing the impact if anything hits the hat. If there's no space in there, and somebody drops a crowbar on your head, the force of the impact will go directly to your head. So you want to check your hard hat to make sure there's a space between the shell and the webbing. Adjust the headband for a good fit, and make sure the webbing isn't broken. The shell should also be checked every once in a while to make sure there aren't any cracks in it. If the shell is cracked, or the webbing is damaged in any way, it's time to get yourself a new hat. Now, in addition to the hazard of having something land on your head, there are some work areas where noise can also be hazardous. Loud noise over a period of time can cause you to lose your hearing. Earplugs inserted in the ears will dull sound and help prevent your ears from being damaged. Earmuffs serve the same purpose. Earmuffs, or Mickey Mouse ears as they're sometimes called, also cover the ears to protect them from noise. Safety goggles are also required in many work areas, particularly work areas where overhead pipes could drip chemicals that can irritate or damage someone's eyes. When goggles are worn properly, they keep dust, flying particles, and splashing liquids from reaching your eyes. Most goggles can be adjusted for a good fit. They should fit snugly against the face. In addition to goggles, safety glasses also protect the eyes. Safety glasses are worn like regular glasses. The lenses are usually made of a clear, durable plastic that prevents objects from directly entering the eyes. Some jobs require that a face shield be worn over goggles or safety glasses to protect the rest of the face. For example, if you use a grinder, a face shield will protect your face from flying particles. If you're handling caustic liquids that could splatter, you may need a face shield, and also a rain suit to protect the rest of your body. Rain suits are often worn when working with caustic materials that could contaminate clothing as well as irritate skin. The suit's made of fabric that prevents chemicals from soaking through to the skin. While a rain suit can protect you from chemical hazards, a dust mask can protect you from certain breathing hazards. A dust mask prevents you from inhaling dust and particles that may cloud the air. It's made of fabric that covers the nose and mouth and filters solids from the air before it's inhaled. But a dust mask provides no protection against hazardous gases. If there's a chance that hazardous gases may contaminate a work area, you're required to wear or carry a respirator. A respirator allows you to breathe without inhaling hazardous gases. The most common type of respirator is an air purifying respirator. This type of respirator has a canister containing special chemicals that absorb or remove hazardous gas as you inhale. Since air purifying respirators remove only one type of gas, they're used in areas where only one kind of hazardous gas may be present. On the other hand, self-contained respirators can be used in areas where many hazardous gases are present. That's because self-contained respirators provide a separate supply of breathing air. This separate air supply also allows the respirator to be used in work areas where there's a lack of oxygen. Well, that covers a lot of protective gear you'll be using on the job. Now, none of this gear will prevent accidents, but it will prevent or minimize injuries if you do get into trouble. So for your own safety, remember to use this gear when you need it, okay? You're probably familiar with the uncomfortable condition referred to as acid stomach. I'm sure you've also seen commercials advertising remedies for acid stomach, guaranteed to neutralize acidity. The way that acid stomach is neutralized is similar in principle to an inorganic process reaction commonly used by industry to treat water. Water is treated to make it neutral so that it can be used in process systems. And after water has been used in process systems, it may also be treated to make it neutral before being released to the environment. In this part of the program, we'll discuss a process reaction commonly used to treat water called neutralization. We'll also see how a typical neutralization reaction is used in a process system. Let's start by defining neutralization. Neutralization is a chemical reaction in which an acid reacts with an alkali or base to form water and a salt. Basically, an acid is a substance that releases hydrogen ions when it's added to water. A hydrogen ion is a positively charged hydrogen particle. It's shown like this. For example, hydrochloric acid is a substance that releases hydrogen ions in water. It also releases chloride ions, which are shown this way. An alkali or base is a substance that releases hydroxyl ions when it's added to water. A hydroxyl ion is a negatively charged particle made up of oxygen and hydrogen. This symbol represents a hydroxyl ion. A common base is sodium hydroxide, or NaOH. It releases hydroxyl ions in water. It also releases sodium ions. Let's look at what happens in a neutralization reaction between hydrochloric acid and sodium hydroxide. During the reaction, the hydrochloric acid releases hydrogen ions, and the sodium hydroxide releases hydroxyl ions. The hydrogen ions react with the hydroxyl ions to form water. But also during the reaction, the chloride ions and sodium ions combine to form a salt, sodium chloride. The amount of acid or base used in a neutralization reaction depends on its strength. The strength of an acid or base is determined by its concentration of hydrogen and hydroxyl ions. For instance, in a strong acid, the concentration of hydrogen ions is relatively high, and the concentration of hydroxyl ions is relatively low. In a strong alkali, just the opposite is true. The concentration of hydrogen ions is relatively low, while the concentration of hydroxyl ions is relatively high. Water is neither an acid nor an alkali. In pure water, the concentration of hydrogen ions and hydroxyl ions is basically equal. The strength of an acid or an alkali is usually expressed in terms of a number value on a pH scale. The numbers on the scale range from 0 to 14. On this scale, pure water, which is neither an acid nor a base, has a value of about 7. Any solution with a pH of 7 is a neutral solution. That is, it's neither an acid nor an alkali. From 7, the numbers on the pH scale increase to indicate degrees of alkalinity. The numbers decrease to indicate degrees of acidity. A strong acid, like sulfuric acid, can have a value of less than 1 on the pH scale. A strong alkali, like caustic soda, might have a value close to 14 on the pH scale. However, if the numbers on a pH scale are taken at face value, they can be misleading. Between each two whole numbers on the pH scale, in either direction, the ion concentration of a solution doesn't change by a factor of 1. It changes by a factor of 10. For example, between 2 and 1, the hydrogen ion concentration doesn't double, it increases by 10 times. A solution with a pH of 1 has 10 times more hydrogen ions than a solution with a pH of 2. The same progression holds true for alkaline solutions. A solution with a pH of 14 has 10 times fewer hydrogen ions than a solution with a pH of 13. Well, now we've seen how a pH scale is used to indicate whether a solution is acidic, alkaline, or neutral. pH measurements are used in industry to help monitor and control neutralization reactions. For example, water is used in many plant processes. Water, which is normally neutral, can become either acidic or alkaline after being used in a process system. Before water can be returned to its natural source, such as a lake or river, it must be treated to make it neutral again. Now let's see how a water solution can be neutralized. We'll start with a beaker of water and this pH meter. When we measure the pH of the water, the meter reads about 7, so the water is neutral. Now let's add an alkali, sodium hydroxide, to the water and stir until it's dissolved. Notice that the indicator on the pH meter is rising above 7. This means that there are now more hydroxyl ions than hydrogen ions in the water, and the solution is alkaline. Now, to neutralize the solution, we'll slowly mix some hydrochloric acid into the solution. Now you can see that the pH reading is decreasing to its original point, about 7. This is because the hydroxyl ions in the sodium hydroxide have reacted with the hydrogen ions in the hydrochloric acid to produce a neutral solution, water. Now, as I said earlier, a neutralization reaction produces water and a salt. In the solution that was just neutralized, the salt that was formed is sodium chloride, or NaCl. Neutralization reactions produce only a small amount of salt, and generally the salt that's formed is environmentally safe. Now that we've discussed the basics of a neutralization reaction, let's look at a simplified illustration of a typical wastewater treatment system and see how it uses a neutralization reaction. This system is designed to neutralize water that's been used by a plant so that the water can be returned to its natural source. The system consists of an acid feed tank, a mixing tank, a pH controller, a control valve, and an acid addition pump. This feed tank holds an acid that's used to react with the alkali in the water. Only an acid is used in this system because the water being treated is alkaline. When a system is used to treat water that may be either acidic or alkaline, the system would include a second tank for an alkali. The acid addition pump supplies the motive force to move the acid through this line to the mixing tank. This mixing tank holds untreated water. It contains an agitator that mixes the untreated water with the acid. The pH controller automatically measures the water's pH and opens or closes the control valve to add the proper amount of acid to the mixing tank. Inside the tank, the acid reacts with the alkali in the untreated water. When the pH controller determines that the water is neutral, about 7, the water can be returned to the environment. And that's basically how the system works. Well, now we've covered acids, bases, and neutralization reactions. We've also seen how a typical neutralization reaction is used in a water treatment system. So far in this program, we've looked at 3 typical inorganic process reactions: ionization, redox, and neutralization. When we come back, we'll start looking at some typical organic process reactions.
In a typical industrial facility, in order to get fluids where they're needed when they're needed requires the use of many valves. Each valve is designed to serve a particular purpose. In this part of the program, we'll take a look at several types of valves: gate valves, globe valves, and needle valves. We'll see how they work and why they're suited for their particular purpose. Let's begin with gate valves. This is a cutaway of one. Generally, a gate valve can be identified by its relatively long body and stem that extends some distance beyond the piping to which it's connected. Gate valves are primarily designed to be used for on-off purposes. In other words, they operate best in either the fully open or fully closed position. However, a gate valve may be used for throttling in an emergency. If a gate valve is used to throttle or regulate flow for a long time, its disc will wear unevenly and prevent the complete shutoff of fluid when the valve is closed. We'll see how this happens a little later. Gate valves are often used to isolate equipment. For example, these gate valves are located in the suction and discharge lines of a pump. The valves are used to block the flow of fluid to the pump, thereby isolating the pump. For instance, equipment may be isolated so that maintenance can be performed on it. Gate valves are also commonly used in situations where the valve position, open or closed, is seldom changed, like this drain valve on a tank. Most of the time, the valve is closed, and only infrequently will it be open. This gate valve has all the parts you saw earlier: a body, a seating area, a disc, a bonnet, packing, a stem, and a hand wheel. Now let's look at the other parts of a gate valve using this illustration. The parts include a stuffing box and a packing gland with gland nuts. The stuffing box holds the packing in place around the stem. The packing gland fits over the stem and on top of the stuffing box. It's used to compress the packing inside the stuffing box to ensure a good seal against leakage. These gland nuts are used to adjust the pressure on the packing gland. As the valve is used, the packing will wear and the valve may leak. When leaks do occur, they can oftentimes be stopped by slightly tightening the gland nuts to compress the packing. Gate valves get their name from the way the disc is raised and lowered like a gate. The disc is usually wedge-shaped and fits into the seating area to stop the flow of fluid. The disc fits snugly in the seat when the valve is closed. When the disc is completely raised, flow is fairly straight through the valve with little obstruction. However, in many types of gate valves, when the disc is raised slightly, a space opens on both sides of the disc. Let's look at an illustration to see what happens when the disc is raised slightly. When the disc is partially raised and remains in the flow path, fluid passes underneath the disc in this manner. This creates turbulence. The turbulence causes the disc to swing from side to side, banging or chattering against the seat of the valve. The chattering quickly leads to wear on the seat and the disc, and eventually, the valve won't shut off flow when it's fully closed. In addition, the flow and pressure of fluid through the valve when the disc is only partially raised wears the disc unevenly. As you can see here, these edges of the disc are exposed to the fluid flow more than the rest of the disc, so the passing fluid erodes this area more than other areas of the disc. The uneven wear on the disc will keep it from seating properly. This design is one reason why gate valves are more practical for on-off use rather than for throttling. Now, the problem with uneven disc wear is eliminated in the design of globe valves. Therefore, globe valves are more practical for throttling. Globe valves have a different kind of disc and seating arrangement from gate valves. The disc is lowered on top of the seat here to close the valve. The parts of a globe valve are basically the same as those in a gate valve. However, on many globe valves, the packing is adjusted using a single gland nut, like this one here, instead of two gland nuts like we've seen on gate valves and the ones on this globe valve. Now let's look at another typical part of a globe valve that's different from most gate valves. Many globe valves, especially those used in steam systems, are built with a back seat. The back seat provides a seal between the stem and the bonnet. When the valve is fully open, the raised disc seats against the back seat, preventing leakage into the upper part of the valve. In this way, the back seat protects the packing from excessive wear caused by fluid flow and pressure. You can recognize a globe valve by its globe-shaped body. The flow of fluid through the valve is different from flow through a gate valve. Let's see how. While the flow through an open gate valve is in a fairly straight line, fluid flow through this open globe valve makes several nearly right-angle turns. So when the valve is open, all of the disc is exposed to the fluid flow. Fluid flow contacts all the surfaces of the disc in the seat, resulting in even wear. Even after the valve has been used for throttling for long periods of time, complete closure is usually possible. This is a type of globe valve called an angle valve. It's easy to spot by its globe-shaped body with connections at right angles. Angle valves are used to change the direction of fluid flow. This design eliminates the necessity of added piping that is normally required to change the direction of flow when other types of valves are used. Now, this is another variation of a globe valve called a needle valve. Needle valves are usually smaller than other types of globe valves and are designed to give fine control of flow in small diameter piping. A needle valve basically has the same parts as other types of globe valves. It's named for its needle-shaped disc, which is sometimes called a needle or plug. The needle and stem are usually a single piece. Notice how the needle goes deep down into the seating area. A small movement of the valve stem causes a small, gradual change in the flow rate. This gives the needle valve its extremely fine throttling ability. Well, now you've seen the operation and some of the uses of gate valves, globe valves, and some variations of globe valves. You've seen why gate valves are typically used in fully open or fully closed positions, and why globe valves and needle valves are especially suited for throttling. When we get back, we'll look at several valves that may be used for either on-off or throttling purposes.
We've already emphasized the importance of filters in industrial process systems. Now we're going to take a closer look at the operation of a type of filter called a cartridge filter. Cartridge filters vary in design and size depending on the job they do. This is a filter tube, which fits inside this cartridge filter housing. This filter assembly is used to filter water. Different types of filter media are used in filter tubes, depending on the fluid being filtered and the size of the solids being removed. The filter medium is the material that does the actual separation of mixtures. For example, the filter medium from this tube is a man-made material wound around a central core. Other filter media used in cartridge filters include special papers and porous plastic. One of the reasons cartridge filters are so commonly used is that the filter tubes are convenient to handle and easy to replace. I'll open this filter housing to show you how easily a filter tube can be replaced. I simply take the old filter tube out of the housing, drop the new tube into place, and close the filter housing cover. It's done. Many cartridge filters are designed with the filter medium permanently enclosed in the housing. They're called disposable filter assemblies. This is a disposable filter assembly used to filter fuel. Instead of replacing the filter medium, the entire disposable filter assembly is replaced. This design saves time and helps minimize contact with fuel. In some applications, it's important to minimize contact with fuel because some fuels are harmful to touch. Now let's take a look at a simplified illustration to see how a cartridge filter works. This cartridge filter consists of seat plate assemblies, filter tubes connected by spacers, and tube guides. All of these parts fit inside the filter housing. This seat plate assembly seals one end of the center core and works with the tube guide to hold the filter tube in place inside the filter housing. Each filter tube has filter medium that surrounds a center core. This center core is a hollow shaft made of metal or plastic. The core is pierced with holes to allow the liquid to pass through it. The spacer seals the center core between two connecting filter tubes. The spacer prevents unfiltered liquid from bypassing the filter medium and leaking directly into the center core. The filter housing consists of cover fasteners, a main housing cover, a cover gasket, a feed line, and a discharge line. These fasteners hold the cover in place. This filter housing cover allows access to the filter tubes. The cover is sealed with a gasket to help prevent leaks. This feed line supplies unfiltered liquid to the filter. It contains an isolation valve. This discharge line also contains an isolation valve. The isolation valves allow the filter to be shut down and isolated when necessary. Feed and filtrate are terms that are common to all filters, not just cartridge filters. There are a couple more valves associated with this filter. This is a vent valve, which allows air to escape the filter. And this is a drain valve used to drain the filter housing. All the valves are used when the filter tubes are being changed. During operation, the feed and discharge isolation valves are opened. Feed enters the filter here and passes through the filter medium. The solids collect on the outside of the filter medium. Then the filtrate flows through the holes in the center core and through the discharge line to the next component in the system. That's basically how a cartridge filter works. Sometimes two of these filters are used when the flow of material being filtered can't be stopped because of process requirements. One filter is in operation and the other is isolated and on standby. In your job, you may sometimes have to replace the filter tubes in cartridge filters. We'll cover this procedure in your text. Whenever you do change filter tubes, always be aware of any special procedures involved in handling the tubes. For instance, the material being filtered may be flammable or dangerous to touch. In such a case, you should know what specific handling safeguards and special protective gear are needed for the job. Your facility may have special requirements for the handling of the filter cake that remains on the surface of the filter medium. In some cases, the filter cake may be valuable and must be saved for further processing. So to avoid costly mistakes, learn your facility's procedures and talk with your supervisor when there's any doubt about what you should do. When we return, we'll look at the operations of a gravity filter and a pressure filter. In the previous part of the program, we looked at three basic distillation systems. In this part of the program, we'll be taking a closer look at a distillation tower and how it works. It's important to remember that so far in this program, we've been concerned only with separating two products from a mixture. A distillation system that separates two products is called a binary system, and that's the kind of system we'll be looking at in this part of the program. Later on in the program, we'll be looking at a system that separates a mixture into many products. To understand how a distillation tower works, let's first look at the distillation system as a whole. Basically, a distillation tower is simply a series of stills placed on top of each other. The mixture to be distilled is heated to its boiling point and pumped into the tower. The heavier component of the mixture moves down the tower as a liquid. Attached to the bottom of the tower is a mechanism for supplying heat to boil some of the liquid that has collected there. This mechanism boils some of the liquid at the bottom and causes it to vaporize and move up the tower. Some of the liquid at the bottom is drawn off as the bottom's product. Meanwhile, the lighter component of the mixture rises up the tower as a vapor. It comes out the top of the tower, is sent through the condenser, and condenses into a liquid. A portion of the overhead liquid is drawn off as the overhead product. Another portion of the liquid is pumped back into the top of the tower. Let's go through the process again by following a mixture as it's distilled in the tower. The mixture to be distilled is first held in a container. This container is called a storage tank or a feed tank. The mixture is pumped to a preheater where it is heated under pressure to prevent it from boiling. The heated mixture is released into the tower through a valve. As the mixture enters the tower, it starts boiling because it's no longer under pressure. The vapors that separate from the boiling mixture rise up and move toward the next higher tray. Each tray has holes, which are fitted with tubes called risers. The risers allow vapors from the lower tray to rise into the upper tray. Mounted on top of the risers are caps called bubble caps. The purpose of these bubble caps is to force the rising vapors to bubble through the liquid that has condensed in the upper tray. Distillation towers contain many risers and bubble caps. This is important because the rising vapors must make maximum contact with the liquid so that maximum heat transfer can take place between the vapors and the liquid. The vapors bubble through the liquid on the tray. Because the liquid is at a lower temperature than the vapors, the heavier parts of the vapors condense as heat transfers from the vapors into the liquid. At the same time, the heat that transfers from the hot vapors into the liquid also causes the lighter parts of the liquid to boil. The lighter vapors then rise toward the next tray. Now, the vapors that rise up through the trays contain a higher concentration of the overhead product and a lower concentration of the bottoms product, which has condensed on each tray and flowed down. As liquid collects, it rises to a predetermined level. This level is determined by a sort of dam called a weir. The liquid then flows over the weir and into tubes called downcomers. The downcomers allow the liquid to flow down to the lower tray. Each tray moving down the tower is hotter than the tray above. When the cooler liquid flows through the downcomers, it collects on the tray below and meets the hotter vapor rising up. The lighter component of the liquid is vaporized and separated from the liquid, while the heavier component builds up on the next lower tray until it overflows and continues to flow down. The section of the tower above the feed tray is called the rectifying section. Rectifying refers to the part of the tower where the concentration of the lighter product is increased. The section of the tower below the feed tray, where the liquid flowing down loses its lighter products, is called the stripping section. The heavier liquid has been stripped of its lighter component. If the tower worked perfectly, it would produce a pure overhead product and a pure bottoms product. Instead, the system typically produces an overlap, that is, an overhead product containing some bottoms product that has vaporized and a bottoms product containing some overhead product that has condensed. The overlap occurs for a number of reasons. For example, tower temperatures are often difficult to control. Also, the two desired products may have close boiling ranges, which make them harder to separate. Distillation towers have additional systems to help produce the best separation. Let's look at the top of the tower first. The process used to help control the overlap at the top of the tower is called refluxing. Refluxing involves reintroducing part of the condensed vapors coming off the top back into the top of the tower. Here's how it works. The vapors coming off the top of the tower are condensed in the condenser. A portion of this condensed liquid is drawn off as the overhead product. Another portion of the overhead product is piped back into the top tray of the tower. The liquid that is reintroduced in this manner is called the reflux. Because it consists of liquid that was cooled in the condenser, the reflux that is pumped back into the tower is cooler than the liquid and vapors in the top tray. It therefore causes any heavier products to condense instead of vaporizing and coming off the top. The heavier part of the reflux itself flows down the tower while any lighter part vaporizes and comes back off the top. The process of refluxing helps make the overhead product purer because it helps prevent the overhead product from containing any heavier bottoms product. Now, at the bottom of the tower, lighter product that has failed to vaporize may have gotten pulled down or entrained in the bottom's product. The process used to control this situation is reboiling. Reboiling provides the necessary heat to make certain that the lighter product is boiled off. It works like this. A portion of the bottom's liquid is drawn off the tower and sent through a heater, called a reboiler. The reboiler heats the liquid to its boiling point. The vapor-liquid mixture is reintroduced into the tower. These hot vapors cause any lighter part of the liquid at the bottom to vaporize and move up the tower. The reboiler is also sometimes used to provide the major portion of the heat necessary to make the distillation process work. The heat supplied by preheating the mixture is usually not enough to make the process work. The reboiler provides enough heat to cause the lighter product to vaporize in the tower. Towers that use reboilers are sometimes referred to as reboiler towers. To make certain that the tower works properly, it's important to control the balance between the liquid going down and the vapors going up. This balance is accomplished by controlling the reflux rate and the boil-up rate. The reflux rate is the amount of reflux pumped back into the tower. The boil-up rate is the amount of vapors reintroduced back into the tower from the reboiler. We'll be talking more about the reflux rate and the boil-up rate later in this program. The tower that we've just seen is just one typical design. It uses bubble caps to force vapors to make maximum contact with liquids. This allows for maximum heat transfer between vapors and liquids and ensures good distillation. There are other ways to get the same result. One of these is to use another type of material to make contact between liquids and vapors. One example is a packed tower. A packed tower works in basically the same way as a bubble cap tower, except that instead of trays containing bubble caps, it has trays that contain layers of packing. The packing material provides a large surface area over which the vapors and liquids can come into contact. This packing comes in many shapes and materials. One common type is a cylindrical ring known as a Raschig ring. Another type of packing is known as a burl saddle. Packing material may be carbon, porcelain, copper, iron, or any other material that will not be corroded by the liquids contained in the tower. Packed towers are simply another method for making the distillation process work effectively. In this part of the program, we've seen how a basic distillation tower works to separate two products. We also looked at a different method for providing the contact area for the liquids and the vapors as they move through the tower. In the next part of the program, we're going to look at two variations of this basic tower. We'll look at a tower that is designed to separate not just two products, but many products from a liquid mixture. We'll also look at a tower that operates not at atmospheric conditions, but under a partial vacuum.